right, welcome infrastructure admins to today's explainer. Today, we are steadily and methodically breaking down a highly testable, absolutely critical procedure. Our exact focus for the session is titled NCP-MCI 7.5.16.2, Removing or Ejecting Nodes. We're going to pull back the curtain and look at exactly what happens under the hood when you remove a node in a Nutanix cluster. The goal here? To prep you thoroughly for the NCP-MCI 7.5 exam. We are going to focus strictly on how to keep your cluster above its fault tolerance, erasure coding, and awareness minimums throughout that massive data migration that node removal triggers. So, grab a notebook, get comfortable, and let's dive right in. Here is our exam prep blueprint for today. We've got 5 main stops on our roadmap. First, why node removal matters. Second, the node removal workflow. Third, RF and EC minimums. Fourth, exam traps and edge cases. And finally, number 5, key facts to memorize. Let's get to it.
Section 1. Why node removal matters.
So before we get bogged down in the complex mechanics of data migration and cluster limits, we really need to understand the real-world context here. Why are we even executing this administrative task in the first place? Well, you might find yourself needing to eject a node for a handful of really common reasons. Maybe you're replacing a failed hardware node, say a motherboard just totally gave up. Or you might need to evict a node that's entirely unreachable or completely powered off. Or, and this happens all the time, you're deprecating older legacy nodes to make way for a shiny new cluster expansion with modern hardware. But listen, regardless of the specific scenario, the paramount goal throughout this entire process is zero data loss. The Nutanix cluster must maintain strict data availability. That means a node removal isn't just a simple, quick deletion. It's a heavily, beautifully orchestrated data evacuation. Now, before we go even one step further, we absolutely have to lock in our acronyms for this explainer because they dictate whether a node can actually be safely removed. First up is RF, or replication factor. Think of this as simply the number of identical data copies maintained across the cluster to guarantee fault tolerance. Pretty straightforward. Second, we have EC, or erasure coding. Erasure coding is a bit different. It increases your usable capacity by using mathematical parity information to rebuild your data if there's a failure, rather than relying on full one-to-one data replication. Understanding exactly how RF and EC interact with each other is the absolute key to mastering node removal for the exam. Section 2. The node removal workflow. Let's see how all this builds into the actual operations occurring when you click Remove Host in the Prism Element web console. Look, removing a node takes time. It is definitely not an instant process. It's a careful orchestration. First off, the system runs a series of pre-checks. It's validating cluster health and making sure you actually have enough usable storage capacity on the remaining nodes to rebuild the evicted data. It's like making sure you have enough seats in the other cars before kicking someone out of yours. Second, your guest virtual machines are seamlessly migrated off the target node. Third, the cluster begins a massive background data rebuild. And this perfectly illustrates Nutanix's approach to security. If you're using self-encrypting drives or SEDs, they are automatically crypto-erased as a built-in part of this process. The key encryption key is permanently deleted, ensuring any residual data left on those drives is completely unrecoverable. It's totally wiped. After that, step 4, the node is sequentially removed from the Cassandra metadata ring. And finally, the host is placed into maintenance mode, and its underlying disks are implicitly removed from the cluster. Done and dusted.
Section 3. RF and EC minimums.
Okay, pay close attention here, because this is perhaps the single most heavily tested concept regarding node removal on the NCP-MCI exam. You absolutely must know exactly what your cluster minimums are, both before and after a node is ejected. Let's walk through our first concrete example. A standard Nutanix cluster configured with fault tolerance 1, or FT1, using replication factor 2 requires a strict minimum of 3 nodes to maintain normal operations. What does that mean for us? It means you simply cannot dynamically remove a node from a 3-node cluster. Why? Because doing so would drop you down to 2 nodes, breaking that strict minimum requirement and putting your data at risk. On the flip side, if you have a cluster configured for fault tolerance 2, meaning you're using replication factor 3, that setup requires a minimum of 5 nodes to function and properly maintain its copies of metadata and data.
Now here's where it gets really interesting. The math changes entirely the moment you introduce erasure coding into your cluster. If erasure coding is enabled on a storage container, your baseline minimums bump up. You must maintain at least 4 nodes, or 4 blocks if you're using block awareness, for an RF2 cluster. For an RF3 cluster with EC enabled, you need a minimum of 6 nodes or blocks. If a node removal would drop your cluster below these specific hardline minimums, the system's pre-checks that we talked about earlier will step right in and block the removal entirely. So, the absolutely crucial point here is this number, 4. Lock this number into your mind for the exam. 4 is the absolute minimum number of viable entities needed for an RF2 cluster running eraser coding. The system is constantly, dynamically computing the longest EC strip size possible based on your specific configuration. It will simply not allow a node removal if you don't have enough viable fault domains left over to accommodate that largest EC strip. No exceptions.
Section 4. Exam traps and edge cases. Now that we deeply understand those minimums, let's expose some of the specific scenario questions and sneaky warnings that the exam loves to throw at administrators. Here is a classic exam trap and our second concrete example. Picture this. You're managing an RF3 cluster that currently has exactly 5 nodes in it. You select one node and click Remove. Instantly, Prism throws you an error saying the cluster needs at least 5 usable nodes. Wait, why? Well, because while an RF3 cluster operates perfectly fine at 5 nodes, removing one would drop the cluster down to 4 nodes. And since 5 is the absolute floor for RF3, the system protects itself. It prevents the ejection to guarantee your data availability. It's a lifesaver, but it can confuse admins who don't know their minimums. Let's talk about another massive edge case. And this one usually involves a bit of manual administrative interference. Once you initiate a node removal, AOS is heavily orchestrating that data migration in the background. So here is a critical exam warning. Never ever manually shut down the controller VM, the CVM, or place it into maintenance mode yourself while the node removal task is in progress. If you manually trigger exit maintenance mode or shut down the CVM, that automated node removal task will just get stuck, and you're going to trigger a major cluster alert. Hands off. You must let the automated workflow handle the CVM state. Moving on, you will also highly likely be tested on the differences between standard removal and multi-node removal. AOS does actually support removing multiple nodes, but there are some strict guardrails you need to know. The system only allows a maximum of 4 nodes to be removed simultaneously from a cluster. When you trigger this multi-node removal, the nodes are pulled sequentially from the Cassandra metadata ring, so one at a time, but the underlying data rebuild happens in parallel across the cluster to speed things up.
Okay, pay close attention, because this perfectly illustrates the most obscure, dangerous trap of them all, the lowest IP address rule. If you remove a node from a cluster with the intention to repurpose it, you have to watch its IP. If the node you eject happens to have the lowest IP address in the original cluster, and then you just go and add it to a new network where it also becomes the node with the lowest IP address, well, the new cluster is going to inherit the cluster ID from the original. This creates a duplicate cluster ID, a split-brain scenario on your network that will completely, totally break your disaster recovery operations. To prevent this nightmare, you must completely re-image the node using Foundation before ever adding it to the new cluster.
Section 5. Key facts to memorize. All right, we are going to synthesize everything we've just covered into the core, non-negotiable facts you need to have instantly recallable for your NCP-MCI 7.5 exam. Let's commit these final facts to memory right now. First, after initiating a node removal, you must always wait for the cluster's self-healing resiliency task to finish completely before performing any other administrative actions, simply because your fault tolerance is temporarily reduced during that time. Second, if you use self-encrypting drives, remember they are automatically crypto-erased during eviction. Third, if you're executing a multi-node removal, the absolute hard cap is a maximum of 4 nodes simultaneously. Fourth, memorize your erasure coding minimums. RF2 needs a minimum of 4 nodes or blocks, and RF3 needs 6. And lastly, beware the lowest IP address rule to avoid breaking disaster recovery. Always re-image those specific nodes before repurposing them.
Now, I'm going to leave you with this provocative scenario to ponder as you continue your exam prep. We know that an RF2 cluster with erasure coding needs 4 blocks to maintain block awareness and parity stripes, right? But if an administrator attempts an ejection that would somehow force that EC-enabled cluster down to just 3 blocks, what exactly happens under the hood to your fault domains? And how does the system react to protect your data reduction? Think deeply about the underlying mechanics of the parity calculation we discussed today. Truly grasping that why is what separates good admins from great ones. Thank you so much for joining me for this explainer, and good luck crushing your NCP-MCI 7.5 exam.